Okay, well, welcome back. This is part 5 in our series on understanding 3D rendering, and we'll be using C++. And these beginning videos are intended to get a good conceptual understanding of all the stuff we're going to be working with, so we don't just jump in and write code and not really know what we're writing. So this video is going to be talking about a very, very important and fairly complex part of our 3D rendering journey. And it's discussing what is a GPU, a graphics processing unit. And GPUs can be very complex, but they are very, very important. So we need to get a good conceptual understanding of what's going on and what they are. So to start out, we're going to fire up GIMP. And this is an image here that I generated with a background. I built this model in Blender and I rendered it out, and then I applied a little post-production stuff to get a blur to make it look like it's zooming around. So this image should help us a bit in understanding what is a GPU and why do we need it. So if you look up top here, you can see that this image is 3,873 pixels across by 2,637 pixels down. So if we get our trusty calculator out here and multiply those two numbers, you can see there are 10,213,101 pixels in this image. And if you don't believe that, then we will scroll in here real close and you can see, yep, it's all made of these blocky pixels. And if you're not real familiar with images, I suggest you check my previous videos. There's 2 videos talking about images and what they're made of and all that kind of stuff. So the point here is that there are over 10 million pixels in this image. And somehow your computer has to calculate R, G, and B values for each of those pixels. All right? So in the previous videos, we showed that every pixel in an image is defined, the color of the pixel is defined by 3 values, and that is a R value, a G value, and a B value. So if you consider you've got 10.2 million pixels and you need 3 values calculated for each pixel, you multiply this times 3, and now you're up to over 30 million calculations that are required to display this image. I need 30 million values in order to reproduce this image. So you got to ask yourself, wait a minute, how am I going to do 30 million calculations every time I send this image to the screen? Well, that's a lot of work. 30 million calculations, and plus there's a whole bunch more going on if we're doing 3D rendering, where you've got to calculate scene quantities and you've got to figure out how the scene is going to look from the camera's perspective. There's a lot more calculations. So you're thinking, wow, that's a lot of calculations. So for this image alone, let's say I've got a CPU, central processing unit, and I start at the top here at pixel 0, 0, and I calculate the 3 values. And then I move over to the next pixel and calculate 3 values and do that for every one of the 10 million pixels. That takes a long time, right? So you'd rather not do this sequentially, pixel by pixel. You know, it would be ideal if you could have a separate set of hardware that can do, you know, ideally if you could have, say, 10 million little calculators that could each simultaneously calculate the R, G, and B values for each pixel. So it's like a big factory, and I've got 10 million workers. And each worker has a job, and its only job is to calculate red, green, and blue for the pixel it's been assigned to, right? That would be great. 10 million workers, and you sound an alarm, you press a button, and everybody immediately, simultaneously calculates the R, G, and B value for its pixel that it was assigned. And then instantaneously, you get the entire image calculated and you can display it on the screen. And that's kind of the idea behind a GPU. A GPU is a step in that direction, where you're trying to break up these millions of calculations into a large number of smaller processors who only do a portion of the image. So you assign just a small portion of this image to a processor, like a mini CPU, and say, okay, you calculate this little portion of the image, and I'll send the rest of the image to thousands of other calculators, and we'll try and break this big job up into little tiny jobs. That's basically the job of a GPU. It's got thousands of little processing units, and it can break up a task into those different values. Now, the good thing about an image like this is the calculation for each pixel is totally independent from any of the other pixels, right? So it's like I've got my 10 million workers in the factory. I can give each worker a set of input data to figure out what the RGB values are for each pixel, and it doesn't have to communicate with any of the other workers. It can just take it in, do the calculation, and spit out the RGB values. That's what's called an embarrassingly parallel problem, where the individual calculations don't rely on the others. They don't have to wait for the guy next to him to finish his calculation before he does his. So he can do everything in parallel, totally in parallel, right? That's the ideal world, where everything can be done in parallel by separate processors. And that's the goal of the GPU, to solve problems that are embarrassingly parallel, where each processing unit works on its own, doesn't have to wait for anybody else, it just does its own work. And this graphics calculation, as you can see, is very parallel. You know, you don't have to wait for anybody else, you just get some input data, calculate RGB, and you're done, all right? So that's the ideal of a GPU. Now, in practice, the implementation is different. You're not going to have 30 million processors or 10 million processors. You're going to have less. And of course, in the real world, very few problems are actually embarrassingly parallel, totally parallel. And in fact, even an image like this, if you're going to do special effects and you're going to blur, you're going to need to have information about the pixels around you to blur, and the embarrassingly parallel falls down. And the problem is, if you don't have a problem that you're trying to solve that is embarrassingly parallel, then, you know, the little calculator people are going to have to wait for the guy next to them, and the whole thing's going to slow down. So while you're hoping everything will be super fast and wonderful, in practice, it's probably not that way for a bunch of different reasons. So ideally, yes, you can have that, but in the real world, unfortunately, real life steps in, and stuff requires that you're not totally parallel, and things are going to slow down. Okay, so we know that we ideally would like to have some hardware that's got many, many processors that can process an image in parallel, simultaneously, rather than pixel by pixel. But there's another thing that we would like, and that is to sit down and look at the graphics problems we're going to solve and optimize the hardware for those particular problems. Okay? It's not just about having lots of processors. It's about having processors that are designed to solve the specific problems we're going to encounter. So as an example, when we're doing ray tracing, all right, one of the steps in ray tracing is to simulate a camera as if a camera is taking a picture of an outdoor scene or something. And what we do is we simulate sending a ray, a light beam, out of the camera into our scene to see if it hits any object. And we do that to determine, you know, how to reproduce the scene on our film. And we have to calculate whether that ray at any point along its length is going to hit any object, right? And we do that millions and millions of times, because we have to do that every time for every of the 10 million pixels. We have to send out a ray, see if it sees an object. If so, what's the color of the object? And then we can say, this pixel sees a sphere with a color of blue, therefore we can put that on the screen as part of the image, all right? Now to do this calculation, it's called a hit test, to see if your ray hits any object. We have to solve what's called a quadratic equation. And the solution to that looks a lot like this equation here, where you take three numbers, A, B, and C, you multiply A and C, and then multiply them by 4, and subtract the result from B squared, okay? So this calculation is done many, many, many millions of times when you're doing ray tracing to determine if your ray, one of 10 million rays, is hitting any object. So you have to do this calculation many, many times. So if you're smart, you'll sit down and say, hey, wait a minute. I want a lot of processors, but I also want a group of processors who are really, really, really good at solving b squared minus 4ac. I give them three numbers, they solve b squared minus 4ac, and they output the answer really quick. So that's another goal of your GPU. You want to figure out what problems you have to solve and design the hardware to solve those problems. Now, just because you have hardware that's designed to solve those problems doesn't mean that your ultimate problem that you're trying to solve matches that, okay? This set of hardware that solves b squared minus 4ac is only good if you need to solve a hit, right? If you're doing something else with your GPU, you're not going to have much benefit from this guy. It's going to look at you, if you have to add numbers, two numbers, it's going to look at you and say, no, wait a minute. I only know b squared minus 4ac. You're asking me to add numbers. I don't even know what add means, right? So that's kind of the concept. You've got your hit guy, your hit man, whose job is to solve this equation, right? And you've got many, many of these in your GPU, and that's all they do. They solve this. So if you've got to solve that problem, you say, oh, okay, let me contact the hitman. They'll go solve this problem real quick. But you don't send them a different type of problem that they're not good at, right? So when you're writing software, you don't want your hardware to go unused because it's always looking for this problem. So it comes down to optimization, and I think people don't get that. Users, hobbyist users, tech users don't get that, just because you've got a high-powered GPU doesn't mean that your software is written to take advantage of that, or that the problem that you're trying to solve takes advantage of that hardware, right? It's got to be optimized, and it's got to be written to be optimized to take advantage of that. So those are kind of the two basic strengths of a GPU. There's many processors, and the processor groups of hardware are designed to solve specific types of problems. So hopefully you can use those two things to your benefit in your software. Hopefully you have a problem that fits this. So, if you're doing video encoding, this is irrelevant to video encoding, right? This hitman problem is irrelevant. So, is your GPU going to be utilized? Maybe not, right? So there's that nuance there that you need to be aware of when you're talking about GPUs. Okay, so the next thing we're going to talk about is GPU performance. And the goal here is to try and get some insight into the real-world performance of a GPU. And I'm going to show you some results after I rendered this scene in an Iray-based, NVIDIA Iray-based or CUDA-based renderer called DAZ Studio. And I'm going to show some of the results of the actual real-world performance of a GPU so we can get some insight into what to actually expect from a GPU and how to actually monitor it, and maybe clear up some confusion on how the GPU works relative to the CPU. So the system I used has a NVIDIA GTX 1080 Ti. And according to NVIDIA, the specs for the thermal and power ratings are that the graphics card power is 250 watts, okay? So you might expect, okay, if I'm going to do a render of a scene like this, my GPU is going to use 250 watts, right? So let's take a look and see what actually happens. Now, before we do that, I want to get a general overview on the process here, how your CPU interacts with your GPU with a renderer like this. Now, keep in mind, this is just a regular 3D render. It's not a game. There's no real interaction other than you set up your scene and you render it, okay? So here's the general steps that occur when you are doing a render like this. The first step is the user or the software loads objects, images, whatever, into the scene, into the user interface, so that the user can modify them, change the lights, change the colors, whatever, the placement of the objects, whatever, and get everything ready for the render. So you load the objects and the images, the user configures the scene, adjusts things so they're ready to render, and then the user presses render, okay? At that point, everything's all set, and the CPU then takes all of the pertinent data from that scene that's going to be needed by the GPU to render it, and sends all of that data via the PCIe bus, which is a fast serial bus on your motherboard, to the PCIe slot where the GPU is residing, and it fills the VRAM, the GPU VRAM, which is kind of like system RAM on a GPU, and it fills that RAM, and it had already allocated that RAM previously, so it fills the allocated RAM with all of the scene data, and once that's all full and ready to go, the GPU goes through all of its calculations to do the actual render. Once that is done, once all the data is sent over to the GPU VRAM, the CPU is pretty much out of it and it goes idle for the most part, right? There may be some interactions, but generally the CPU is pretty much idle, depending on the renderer and everything else. But so basically the CPU is very active, getting everything ready. It sends everything over the PCIe bus. Once everything is sent over, the CPU is done. It kind of goes off and does other things. The PCIe bus is pretty much dead or idle because it's already transferred everything. And now the GPU does its work. Okay? So let's look at my task manager for the NVIDIA GeForce GTX 1080 Ti at the beginning of the render, and you can see what's actually happening. So here are four graphs that I'm plotting for the various GPU engines that we discussed in the previous video. And I've got the Compute 0, I've got the CUDA engine, I've got the copy engine, and the 3D engine, all right? So if you were, at first thought, if you're going to do a render, you would think, it's a 3D render, therefore the 3D engine would be real busy. Well, no. Keep in mind, this is an NVIDIA iRay CUDA-based render, so apparently they are using this CUDA engine, all right? So you can see in the beginning, it shows that the CUDA engine and every other engine is pretty much idle. And you can see that the VRAM, here's the dedicated GPU VRAM, there's a maximum of 11 on this card. And you can see at this point it's up to about almost 4, it's 3.9. Just before this point it was very low, it was down at 0.5, and that was before the CPU had transferred the data over the PCI bus. But I didn't capture the part where it filled up the VRAM, but you get the idea, right? Somewhere over here it filled up the VRAM, and then once that's all full, the CUDA engine, the GPU gets very busy on the CUDA engine to actually do the render. And you can see it immediately slams up to around 100%, bouncing around a little bit, few percent. But basically, it's real busy doing 100% doing the render. Okay? At this point, the CPU is pretty much idle. I mean, 26%, but as we'll see, Actually, there's a bunch of threads that are idle, and there's a couple threads doing some stuff. All right. So here is it's an 8-core, 16-thread CPU, and you can see here's the 16 threads, and a bunch of them are pretty much idle, and there's a couple that are doing some things, but basically there's not much utilization of the CPU. Again, it's handed everything off to the GPU, and it's kind of wiped its hands and said, okay, I'm done, I'm busy doing other things, okay? Now, what I did is I used GPU-Z to plot some of the performance data of my GPU. All right? And I've got two graphs here. The top one is power consumption, and the bottom is GPU load. And this is logging the power consumption and load for the full 40 minutes of the render. It took about 40 minutes to render this, and here is the data for power consumption and load for the entire 40 minutes. Now, prior to this point, you can ignore this. I forgot to reset the logger, but basically it's pretty much 0 here and 0 here, I think. So you can see right at this point, it matches the task manager and shows that the GPU load utilization is about 100% and stays flat for 40 minutes. Now, the power consumption at the same time is bouncing around 180 watts. Now, you may scratch your head and say, wait a minute, we saw a NVIDIA spec for that card that says 250. Why are we only 180? I mean, sometimes it bounces up to 200, a little above 200, but the average is around 180. Well, that's because, as I mentioned before, just because the spec says 250 doesn't mean it's always going to run at 250. It depends on the software, right? Does the software take full advantage? Does that scene require all of the cores of the GPU, right? Can the software and the scene that you're working on actually utilize the entire GPU hardware? And in this case, clearly it doesn't. Right? Because it's only 180 watts, it's not 250 watts. So it's not meeting the total maximum capacity of the GPU, and that's probably something between the software, the iRay renderer, and the scene itself. Maybe the scene itself doesn't utilize, the contents of the scene don't utilize the GPU engines to 100%. So again, don't believe the specs, actually measure stuff, all right? Now, this down at the bottom is a measurement of the entire total watt consumption of my entire computer at this time, and it's 280 watts, all right? So my GPU is 180 watts, and the total computer is 280 watts. So there's 100 watts missing here. You would think that, it'd be 250 watts and only 30 watts, but no, there's 180 watts and there's another 100 watts missing. So this reflects what the CPU is using, and I recall that was around 30 watts, what the motherboard is using, losses in the power supply, usage by the power supply. So all of those other things add up to about 100 watts. So it's really good to actually measure stuff and not assume stuff, and know how to measure this stuff, and have the tools that you need to actually measure this stuff, and it will really help you to understand it a lot better. So that's about it for this video. We may go into more detail in the next video on GPUs, but I hope this has been helpful and helped you to learn a little bit more about GPUs. So take care and have a really good day. Thanks.